Hi there, welcome to lecture 11 of Machine Learning from Data, Overfitting. Now that's a buzzword, but it's not just a buzzword. It's what differentiates the professional from the amateur. So if you can get a grip on overfitting, that's going to raise you to the level of a professional. Now, last lecture I left you with this interesting situation where on the left I'm showing you a data set that's almost linearly separable. So linearly separable modulo a few outliers. And on the right I'm showing you what happens when you throw the fourth order polynomial transform at this data. Gets in-sample error 0, but you look at this and say, really? It looks like nonsense. There's no way that the out-of-sample error is anywhere close to 0. I mean, it just looks contorted and unreal. Okay? And that actually is the typical case of overfitting, where you take this complicated, learning model, this fourth-order polynomial transform, and you throw it at a small data set that has a little bit of noise, and then you get nonsense. Okay? That's what we're going to study today. Now, before we get going, let's do our usual thing and recap where we were from last time. Last time we discussed the mechanics of the nonlinear transform. Now, at a high level, the nonlinear transform allows us to leverage all the power, the convenience, the algorithms from the linear model, but still get a nonlinear classification boundary in our original X space. And here's how it works. Okay, you start with your data that's clearly not separable by a line. Okay, and what you do is you construct a feature transform, a nonlinear feature transform that transforms this data to a new space. This new space, the feature transform space, we call the Z space. Okay? And lo and behold, in this Z space, the data is separable by a line. So you can go ahead and run your PLA or pocket algorithm or regression for classification, whatever your favorite linear model algorithm is, and find a linear classifier. Now, the thing is that this linear classifier only lives in your feature transform space. And so when you get a new test point in your original space, what you do, you transform the point using the same phi. You transform that point into your Z space, into your feature space, okay? And see, when that point is transformed into your feature space, it'll be either in the red region or the blue region, and you classify accordingly. Now, if you play this game with all possible, test points, some of them will be classified blue, and some of them will be classified red, and that, creates a separation boundary, the classification boundary, which in this case is something like an ellipse. Okay, so let's see what we have achieved. We have managed to get a nonlinear classification boundary in our original space, but we only had to deploy the linear model, albeit in a perhaps more complicated feature transform space. Okay. So the feature transform space, by the way, is under the hood. Okay, so your client comes to you with your original data, you transform, you separate with a line, and then you're ready to go for your client. And when your client looks at what you're doing, it looks like you're doing something very sophisticated and nonlinear. Little does your client know that under the hood is just a linear model, but with this powerful feature transform added on top. Okay. And since it's so powerful, it's now given you the ability to use linear models and get nonlinear classification boundaries. That's an amazing amount of power. You have to use it very carefully. Be careful. Lastly, I'll show you the digits data one more time, to which we applied the linear model, and we got an out-of-sample error approximately 2.4%. Importantly, in-sample is close to out-of-sample because it's the linear model. The linear model is good. Okay, use the linear model. Okay, and that's just with these two features of symmetry and intensity. Something like 97.6% accuracy. Pretty high, right, with just the linear model. Now we come and add the third-order polynomial transform, and because we have enough data, you can still control E in to E out. Okay, even though we've gone to a much higher dimension, you get a nice separator that looks, more reasonable perhaps. Okay, and we've managed to drop the out-of-sample error, which is still close to the in-sample error. We've managed to drop it down to 1.87. So we went from 97.6% accuracy to 98.1% accuracy or something like that. We've improved the accuracy by approximately, 0.5%. Wow, all that work for 0.5%. And you might be thinking, I'm a machine learning expert and I've come with my powerful nonlinear feature transform and I've got just 0.5%. Yes, don't laugh at that 0.5%. Okay. Sometimes that 0.5%, that little bit of extra improvement that the expert, the professional brings along, that little bit of improvement is what's the difference between getting none of the business and getting all the business. So let me give you an example. Think about Google back in the day, 2025, also years ago. In those days, there was InfoSeek, Excite, Yahoo, and what are these things? You probably don't know. Maybe you know what Yahoo is, but InfoSeek, Excite, does anybody know these things anymore? They were all search engines. Okay, they were having they were all competing with each other, competing for search engine business in some sense. And then Google came along. Google wasn't spectacularly better. Now, of course, it's much better than it was, but it wasn't spectacularly better then, but it was a little bit better. And that's the way humans are. When something comes along that's a little bit better, you don't, split your business. You just go all out for the better guy, even though it's just a little bit better. We don't go to Google 80% of the time, and then when we want to search something like monkey pajamas, maybe we go to Yahoo. No, we don't. We go always to Google, no matter what it is. And so, a little bit of improvement is the difference between none of the business and all of the business, and that's a very lucrative business. So don't laugh at this 0.5%. That 0.5% that the expert adds is sometimes the whole deal. Okay, now let's talk about overfitting. Okay, so let's start our discussion of overfitting with the human ability to overfit. Now, we're all familiar with superstitions. Take Friday the 13th. Okay. Maybe historically there have been some bad events that occurred on Friday the 13th. For example, King Philip IV arrested all the Templars on a Friday the 13th, and then they were subsequently executed. So some atrocious things happened on Friday the 13th. Okay. Now, humans are very good at at latching onto these atrocious things. They make a big impression in our mind, and we don't view these as coincidences. We're looking for an explanation. And then when we find an explanation, Friday the 13th are dangerous. Okay, we're happy. We look no further. Okay, we've solved the problem. Okay, we've overfit the data. Are Friday the 13th in the future really going to be more dangerous? I doubt it. In fact, I'm willing to say that perhaps they'll be safer because everyone's so involved in this Friday the 13th fear that they're more careful. And there's even a Greek word for the Friday the 13th fear. Paraskevedekatriaphobia. I don't know if I said it right. But once you give something a word, man, it's got to be real, right? Maybe it's overfitting. Let's talk about OCD. Now we're switching gears to the medical side. And I got this citation from a medical journal, which I've since lost. So if anyone can help me find the citation, I'd be very grateful. Okay, but let me quote. The subject performs an action which leads to a good outcome and thereby generalizes it to cause and effect. The action will always give good results. Having overfit the data, the subject compulsively engages in the activity. And they use the language, having overfit the data. So it's conjectured that OCD may be a phenomenon that arises due to the human's ability to overfit, the human neural network ability to overfit. Now, let me interpret this for you in an example. For example, you want to go outside, and one day you accidentally turn the knob 3 times, the handle, okay, and you open the door, you go out, it's a beautiful day, 70s, you have a great walk. Next day, you forget, you don't accidentally turn the knob 3 times, you go out, you slip on a puddle, you injure your back. Oh my goodness. Now you're in bed thinking, wow, what did I do to deserve this? And then you think, what? Remember yesterday, I turned the knob 3 times, everything was great. And then today, I forgot, I didn't turn the knob 3 times. It must be the turning of the knob. So the next day you go out, make sure you turn the knob 3 times, because obviously you don't want to fall and injure your back. Lo and behold, it's a great day, you have a great walk. Now you've reinforced this overfit hypothesis. And you'll continue turning the knob 3 times a day, further reinforcing that whenever you turn the knob 3 times a day, good things happen. And so now you have become obsessive and compulsive with this. And it's all because you overfit the data. So humans are overfitting machines. We are very good at finding coincidences. And then looking for rational explanations. Okay. Now let's try to pin this down for machines. Okay. And I'm going to show you the typical scenario in which overfitting occurs. So here's a blue target function. It's a quadratic. Okay, I created 5 data points, and what's interesting about these data points is I've added a little bit of measurement error, so the data points are not quite on the blue target function. And since there are 5 points, a 4th order polynomial has 5 parameters, so let's try to fit with a 4th order polynomial, and you get nonsense. It's not even the case that, sure, the fourth order polynomial fits my 5 data points exactly, but it doesn't even get the right behavior as x goes to plus or minus infinity. It's going in the opposite direction as the true, blue target function. So we are nowhere close to f. We have not learned at all. And this is the classic example of overfitting. E in is 0, E out is huge, okay? And, it's because you've thrown a very complex model at a very simple, 5 example data set. But let's pause a little, think about it a little more. Let us, play the thought experiment. What if the noise was 0? So what if I didn't add little measurement error? So now the 5 data points are on the blue curve, okay? And there's a result from mathematics algebra, which says that 5 non-degenerate points can be fit uniquely by a 4th order polynomial because you have 5 coefficients to set, you have 5 data points, and you get 5 equations and 5 unknowns you can uniquely solve. Okay, so there's a unique 4th order polynomial for any 5 non-degenerate points. If the 5 points lie on this blue target function, then the quadratic target function itself, fits all 5 data points. It is a 4th order polynomial, albeit with some of the coefficients 0, but that's fine. Okay? So then that means that this target function must be the unique 4th order polynomial that will fit any 5 data points that come from the target function. What that means is that when you fit a 4th order polynomial to the data, it will reproduce the target function, and you will have learned perfectly. Okay? So it's not just that the 4th order polynomial is too complex. The noise, the little bit of measurement error, that was very devious of me. That has made all the difference. That is what, created this red nonsense. Okay? So it's actually the coupling of the noise with the excessively, complex 4th order polynomial that ends up creating this disaster, and we need to pin it down. Let's first define overfitting. Okay? In a sentence, overfitting is fitting the data more than is warranted. I've highlighted the words more and warranted, and so let's see why I've highlighted the words more and warranted. Okay. And I'm going to show you a picture that we've seen many times. On the x-axis is the VC dimension, and the in-sample error, as you give me more and more complex hypothesis set, the in-sample error is dropping because I have more flexibility to fit the data. Okay. And, the VC analysis tells us that there's this link from in-sample error to out-of-sample error, and that's what we observe as this gap between the out-of-sample error and the in-sample error. And you observe that this gap is increasing, which means that there's bad generalization. The in-sample error is not, the link to the out-of-sample error is getting worse and worse. Okay? And that's what the VC analysis gives us. Okay, the VC analysis can be loose, and so this bound can be loose, but that's more or less what the out-of-sample error is doing. Why is this gap, why is this bound increasing? And we are now very familiar with it because the error bar depends on the VC dimension and increases as you increase the VC dimension. Okay? But that's just bad generalization. And why do I say that that's just bad generalization? It's because, what's happening here? As you give me a larger and larger VC dimension, I'm getting the in-sample error lower and lower, i.e. I'm fitting the data more and more. And as I fit the data more and more, I'm getting lower and lower out-of-sample error. And that's great, because that's all I care about is the out-of-sample error. So it's not a bad idea to fit the data more and more. So what's this business about fitting the data more than is warranted? And we get that when we continue to increase the VC dimension. So now we continue to increase the VC dimension. We continue to fit the data more and more, getting lower and lower in-sample error. But now the out-of-sample error goes up. So now, as we fit the data more and more, okay, we are getting a worse and worse final hypothesis. So fitting the data more and more in this regime is not warranted. It's a bad thing. That is overfitting. So this region where you go for lower and lower in-sample error and it results in higher and higher out-of-sample error is the overfitting region. Okay? So we like fitting as long as it doesn't produce a higher out-of-sample error. And once fitting the data starts producing a higher out-of-sample error, we say that we're starting to overfit. Now, being able to handle, understand, and sort of fight overfitting is what separates the professional from the amateur. So it's worth spending an entire lecture trying to pin down exactly what's going on when overfitting is happening. And so we're going to move to the board.